Swayam Prabha. Digital India. Educated India.
Okay, so we'll come back to an example here in a minute where we bring in the calculations with torsional buckling and so forth. But I'd like to talk a little bit about plate local buckling in columns, and then we'll talk about the unified effective width method, how that works. Again, I'm very interested to talk to Professor Kalyanaraman, and I'm curious where the new IS 801 is going in terms of, is it going to be more like Eurocode or more like the US code, particularly since he was involved with a lot of the developments that led to the US codes. Plate local buckling in columns. So a few definitions of terms. Not sure I remember from my read of the Indian Standard if these are the terminologies in the Indian Standard or not. So in the American Standard, we say if, it's something different than I was about to talk about. So we refer to as a plate element as a slender plate element in uniform compression if we could potentially get buckling locally of that plate before we reach the yield capacity of the cross section. Okay, so would that be slender in the Indian Standard? Okay, yes. Okay, so then the other definitions I was thinking about here. If you have something like a web of an eye section, where you could say that web plate is supported by the flanges on each of its longitudinal edges, AISC calls that a stiffened element. Okay, is that what you would call it in the Indian Standard? Yeah. In the Bridge Standard, we moved away from this because in the Bridge Standard, AASHTO wanted to go in the direction of basically being able to support design of anything from an HSS section up to a massive bridge tower with longitudinal stiffening. So clearly a plate with longitudinal stiffeners on it is different than what AISC is calling a stiffened plate. Well, I brought up unstiffened first here. So that would be like a flange of an eye section. Was one of the edges is free, the other one's is supported by the web, and so that's an unstiffened element. In the Bridge Standard in the Americas, we'd say that's an element that is supported on one longitudinal edge. Okay, and stiffened, that's where I was going there all along. That would be like your web in an eye section. Both edges of the web are prevented from lateral plate bending movement by the flanges, or restrained from lateral plate bending movement. So we have slender plates, unstiffened plate elements, stiffened plate elements. That's AISC's definitions. So then there's tables in AISC, and so basically, how do we define where we are? We look at width to thickness ratios and compare those to limits. And so this table shows some of those limits, and then I'm going to kind of zero in on cases 1 and 2 here in the next few slides. So this is looking at the case with flanges, and when are flanges slender or non-slender. Slender means it's susceptible to local buckling before we can get to the yield load, and non-slender meaning no, we don't need to worry about any local buckling even before getting up to the full yield of the cross section. So here's the case 1. It corresponds to a rolled eye section flange, and so the limit is written in AISC as 0.56 square root E over Fy. I think in the Indian Standard it has an epsilon term like the Eurocode. So we don't have the epsilon in all. We normalize everything directly to a square root E over Fy when we're writing these limits. And if you look at grade 50 steel or 345 megapascals, that works out to 13.4 for and that's the width. We call it B over T generically, but for the flange, that's the half of the width divided by the thickness of the flange that we're using for the width to thickness ratio. Now, it turns out there are no rolled sections that have flanges that are grade 50 steel, grade 345, that would basically classify as a slender flange in uniform axial compression. I think that's there in case as we move to higher yield strength, and so we may get, and you have to have a pretty darn high yield strength before that would kick in though. Now webs is a different matter. Oh, wait a minute, I keep wanting to go to webs before I finish talking about flanges. So if it's a 3-plate welded I section, then we use a different equation because there the web thickness can vary quite significantly depending on what the application is. And so there's a term there that's referred to in the American Standard as K subscript C, that is, we calculate it as 4 divided by square root of H over TW. But if that becomes less than 135, that becomes less than 135 if H over TW is greater than 131. In that case, we limit the minimum calculated value to 0.35, and we don't allow use of a value larger than 0.76. It has to be a very thick web to get to that. So if we have Fy is 345 megapascals, and if we have a very thin web where H over TW is greater than or equal to 131, this limit is 9.1. And so that can trip up a lot of flanges you might want to use in terms of design. Okay, so we finally get to the web, the stiffened elements that I keep thinking of wanting to talk about. So this is the table that kind of shows some graphics with the equations for the different width to thickness ratios that we check here. And if we're looking at I-section webs, so these are 2 cases here, cases 5 and 8, either for rolled or welded. B over T is H over TW here. If it's a rolled section, we take H as distance between the insides of the flange fillets. If it's a welded section, we just go inside to inside of the flanges to calculate H. And we compare that to 1.49 square root E over Fy. So again, if Fy is 345 megapascals, that's 35.9. And so there, if you have, one way to classify I sections is column type I sections, beam type I sections. So column type I sections would tend to have a width of flange and very similar to the depth of the section. And most of those would often have a B over T or an H over TW less than 35.9. But if we get more into the beam type sections, those are sections that are intended more for flexure, and so they're relatively deep in the flange compared to the width of the flanges, and so you can get rolled wide flange sections that have depth to width of the flanges in the order of about 3. There's quite a large number of those would classify as having a slender web and uniform axial compression. So you know, if we have an application that's really dominated by flexure, so we're using a deep section to handle the flexure, but it's also got a little bit of axial load in it. When we do the axial capacity calculation, we end up needing to address local buckling under axial compression. So I said this just a second ago. All wide flange shapes have non-slender flanges, the ASTM wide flange shapes under uniform axial compression for A992 grade 345 steel. Only one column type wide flange shape has a slender web under uniform axial compression. So in imperial terms, that's a W14 by 43. But again, a very large number of the beam type wide flange sections would have slender webs in uniform axial compression. I keep saying slender webs in uniform axial compression because when we go to flexure, it's a different thing. We talk about compact, non-compact, and slender elements there under flexural compression. So it's a different beast when we get to that. With the plate local buckling strength, it's useful to understand theoretically when would a plate that's flat and subjected to uniform compression. That's an interesting academic exercise to say, okay, if we tried to write provisions that would basically work let's work from the stress state in the plate, considering it's a combination of flexure and axial compression. What do we get? So the Eurocode, you can take the Eurocode provisions, which you probably know, and try to do that exercise to get strengths, but then it becomes a very good academic exercise, I would say, right?
Actually, in the new
Yeah.
Indian code also this code came.
Okay.
Seismic detail
Okay.
design for steel structures.
Okay.
So in that code also we have two tables. Like
Okay.
Table. The D by TF based on this one.
Okay.
For ductile member, it will be reduced to like 13.5 became like
Okay.
11 or 10.
For the flange.
Yeah.
For the flanges. Okay. Okay. Very good.
But if we just see that for plastic sections, it is coming around 7.
Okay.
D by TF.
Okay.
Here it is like in the first class.
All right.
Here we
All
are
right.
only just separating slender, non-slender.
Yeah. We're kind of jumping to flexure, but when we get to flexure, I'll tell you that what we call compact flange in the U.S. practice is a class 2 section. What code is that? That's the Indian standard for seismic?
Yeah.
Okay.
18162.
Okay. All right.
I believe they were using the new AIC 341
Okay,
versions
yes.
where they reduce the limits.
Okay. I'm familiar with the web equations there,
Right.
which would give you some benefit.
Right, I think, but the new code, new 341, I haven't looked at it, but I heard that it reduced the compact limits.
The
341.
for seismically compact
Right.
flange.
Yes. And basically,
they
I
may
think the
have.
Indian codes were going off of
I
that
see.
recommendation.
Okay, so now you're saying, okay, hey, what'd you do?
But
Okay.
interestingly, when I
All right.
was at UCSD
Uh-huh.
last fall,
All right.
and I was talking to Professor,
Wang?
yes,
Okay.
and he was conducting a lot more tests now on more sections. He
Okay,
said
good.
because he got a lot of pushback when they reduced those limits.
I see.
And
Okay.
he said people were up in arms and
All right.
fighting that the limits had become too stringent.
Too
and so
strict.
he's trying to see if he
Got
can
it.
relax those a little bit.
Okay.
further.
Okay. Good to hear.
This size code is also exactly the values if we calculate.
Yeah, but this is different for ductile. So you're talking from the seismic. So he's talking about non-seismic.
Right. Yeah. This
so
is
you-
all just getting
in-
strength here.
Yeah, this is just yeah.
The related to that, there's been a group led by Professor Lehman at University of Washington and Professor Judy Liu at the University of Oregon. And a whole group of researchers, and they've been focusing on seismic compactness for box type sections and HSS type sections. And so they're bringing forward from some fairly substantial changes there. I think mostly, and I think in some cases they're liberalizing some of the requirements. They've been bringing that forward very carefully, and I don't know how many different informational meetings they've had for the specification committee on that. And then all the stuff that we're bringing forward on lateral torsional buckling, Dr. Schaefer says, "Okay, all right, we'll show it to them very quickly," and they'll say, "Okay," and we'll move forward. All right. So different approaches. All right. So So these are compactness limits here on the webs. Again, as I was saying, for wide flange shapes, there's nothing that's non-slender for uniform axial compression. There's one column type shape there that's slender, but then a lot of beam type shapes that would classify as slender when we're looking to calculate our strength here. And so then we're about to look at our plate local buckling strength curve, and we'll drill down into some of the things that we're looking at here a little more tomorrow. So several things going on here to interpret here on this plot. So the horizontal axis of the plot is basically stress level at the edges of the plate, if you wish, divided by an elastic buckling stress. Now, the simplest way to maybe interpret this table first is, let's just say, okay, we're going to look at a situation where we develop Fy at the edges of the plate. So square root of Fy over Fe for local buckling. Replace little f by Fy. And then the vertical axis is ratio of the overall capacity Fn on the gross area to F, or that would be equal to the ratio of the effective width to the total width. And then there's one equation that's basically the ratio of Fe for local buckling to, again, little f, which, again, replace that for Fy is the simplest way to understand it here first. And so the green dash curve is the best one to start with. So that's this curve. So that green dash curve is the strength that corresponds. That's when a plate that's theoretically perfectly flat, subjected to uniform axial compression, will buckle out of plane. Then if we go to the next curve up, the dotted blue curve, that's basically a strength that von Karman recommended back in the 1930s. So we're talking about early aircraft design, rockets, things like that. So we would have a plateau strength there, and then you say, okay, we're going to count on some post-buckling strength. Now, we know that when we talk about plate buckling, so you have supported longitudinal edges, and when the plate buckles out of plane, you develop membrane stress in the transverse direction. So that's quite helpful, and you can develop much higher stress than just that stress corresponding to initial buckling out of plane. And so if it's a fairly slender plate, very thin compared to the width, you can see out here at 2.5 for the normalized slenderness, we're getting more than double the strength, considering von Karman's representation than what we'd have for plate local buckling. So then other curves that we're going to see in the American standard, there's the term that's basically, or the curve that's basically the dashed light blue lines. That is essentially what the Eurocode does. That's what we call Winter's equation. The coefficient there that I'm pointing at, C1, is 0.22 there. But in the Americas, with HSS sections and with other things over a period of time, contributors to the specification, we have to go back like 30 years or so, would say, hey, we get HSS section with that rounded corner, that's a little bit different. I've got a web connected to heavier flanges. Yeah, I should get some restraint from those flanges. And so we've played games with that coefficient, where in Eurocode you just always use 0.22. And we like to knock that down to either 0.2 or 0.18, depending on the element that we're talking about. And so that changes the curves a little bit. It gives you the dot dash orange curve or the dotted black curve. But I keep telling my colleagues on the specification committee, when I look at that, I see one curve. Why don't we just go back to using Winter's curve? And then folks will say, well, you actually get a little bit of benefit for that. Here we're on a plate where it's transitioning from non-slender to slender. Oh, okay. All right. So you can see now what's going on here is basically Professor Winter recognized that you would get significant post-buckling strength with a plate, but only when it's very slender. So that's your curves out here. We've got significantly more strength, and still more than double out here at 2.5 than the theoretical elastic buckling strength. However, here in this intermediate range, we've got a residual stress and geometric imperfection problem, and these equations from Professor Winter are basically a reduction on von Karman's predictions to account for residual stresses and geometric imperfections. So from a layman's point of view, I can look at this and say, when I have plate local buckling, kind of looks like a column strength curve, but my strengths out here for very slender lengths are actually much larger than the elastic buckling strength. Then there's one last curve here, that's the black curve, and that shows up only in the bridge standard in the US. And quite frankly, the black curve is something where we, in developing provisions for being able to design massive longitudinally stiffened boxes and things of that sort, we're relying on finite elements for kind of understanding what we were dealing with, not really a chance to do experimental testing on a massive box. After failures in the 1970s, there were actually some very expensive testing works that were done in the United Kingdom on boxes. And a lot of that work, I think they were being very cautious after those bridge failures in the 1970s, had recommendations. But then also there's some more recent German work that suggests that maybe Winter's equations were a little optimistic. And so when we were looking at all that with bringing forward provisions for designing massive longitudinally stiffened boxes and, say, bridge towers in the bridge standard in the US, we decided, okay, yeah, we don't want to be pulled out of our grave because some signature bridge failed because we screwed up in the standard. And so we went with the more conservative UK results for the plate local buckling strength, the black curve here. And we did that by just doing a very simplistic reduction from Winter's curve. All right, so it's often useful to basically say, well, what does plate local buckling look like? If it's a stiffened plate, basically we get to a point, if we take a plate, we support the longitudinal edges, we put it between heads of a test machine, we compress it. At some point, that plate is going to buckle out of plane. Well, if it's got initial imperfections, then it's going to start bending out of plane as soon as we put load on it. But then at a particular load level, those out-of-plane deflections start becoming significant. We get these waves that are forming in the plate. And so we have a situation where the supported edges, the edges kept straight by the supports, so that tends to be stiffer. We're developing higher stress at the supported edge. However, out in the middle of the plate, where we're in the middle of the local buckling, we're tending to be more flexible in terms of longitudinal compression. So therefore, we tend to develop less stress out in the middle of the plate. Well, it'd be rather complicated in design to work with a stress distribution that's some smooth function to represent this. So what do? We basically say, okay, well, we're going to discount the effectiveness of the plate out in the middle, So we've got a total effective width that has two halves here. Again, if you take little f and say, okay, if it's just a plate, if it's not in a column, take f equals to fy. So, okay, my strength of the plate would be when I develop fy at the edges, but I'm going to lose some effectiveness of the plate for its strength out in the middle, right? So that's basically, that's what plate local buckling looks like. That's how we're quantifying things with effective widths. Also, it's useful to understand buckling coefficients for plate local buckling. So this is a plot that's in the Bridge Design Handbook, but with credits to a steel design textbook in the U.S., Salmon and Johnson. We can write the plate local buckling coefficient or equation in the way that you see here, 0.9E times Kc divided by B over T squared, which is what we get if I come back here. This is the equation we usually write from theory of elasticity, but if we plug in 0.3 for Poisson ratio and do pi squared over 12, 1 minus Poisson ratio square, we get essentially 0.9. So now this form, depending on different boundary conditions, we have different values for the local buckling coefficient, Kc. And so we have illustrations of what happens both with different longitudinally supported edges, and then if the loaded edges at the ends are fixed or simply supported. So what you see here is basically what the way we quantify things for design. If we do a analytical calculation, depending on where we land with the aspect ratio A to B, we could have larger strengths, but we typically design for the minimums that we get out of all this. So at a particular A over B, we have a worst case situation and we just count on that to make our design easy in most stuff. And so if you have full rotational restraint on both longitudinal edges, you're case A. If it's fixed, simply supported, it's case B. If it's simply supported edges, case C. So that's very common approximation. Case C is 4. If it's fixed free, it's 1.28. And then if it's simply supported and free, it's 0.425. And so we play various games with that for flanges of I sections in terms of what's our Kc there, in terms of how much restraint do we get from the web. For a very thin web, we actually count on a Kc of 0.35. I showed that to you earlier, 0.35. So that basically means we're saying that the web is going to destabilize the flange in that case. All right, so what I'd like to do is to wrap up today with basically a discussion of things that actually came from Dr. Timon Pecos at Cornell, and Dr. Kalina Raman was very involved with much of this work during his research. The unified plate effective width approach. And so this is an approach where we use effective widths for all elements of the cross section. In some codes, we still use essentially what are referred to as form factors to account for local buckling. Well, the AISC code has moved entirely away from that to using effective widths for everything. If there's a slender cross-section plate element, we calculate an effective width. So the way the unified effective width approach works for a column is we do the column calculation to get an F critical, or I need to update my notation here. The AISC specification now calls that Fn. So that's your strength of the plate. We're trying to, I think I mentioned it the other day, we're trying to move in the direction where subscript CR always means elastic. We're not there yet. And then, so you do that calculation of Fn, or I'm showing it F critical here. That's your column strength formulas that we've been talking about. You do that calculation with gross area to get an Fn. Once you have that, you also need to determine what your effective widths are for your plates. You simply multiply your effective areas by, you get your effective area by summing your effective widths times thicknesses, and multiplied by Fn, you have your column resistance, your nominal resistance. So just to show the equations in AISC look like this. So the middle equation there is what throughout the world we call as Winter's equation, at least when we use a C1 of 0.22. But again, we play games with that and try to gain a little extra benefit for some cases. For instance, for square and rectangular hollow structural sections, we use a C1 of 0.2. And if it's any sort of other stiffened element, you will use 0.18. And the other equations here, we've got an equation for an elastic local buckling stress. I have some handouts for you that explain where all this mess comes from. It's a way of trying to write the elastic buckling stress in terms of the non-cylinder plate limit, lambda r. And so we have limits here when we basically take the effective width equal to the full width. Well, that's when this equation is satisfied. And so what's going on here, if you have a long column, then your Fn, or F critical, of the column is going to be relatively small. We feed that into this equation, and so the logic is, oh, my column fails at a very low stress. I use that stress to check whether I have a local buckling issue or not. And I get my effective widths based on that. Then I multiply that by the Fn, I've got my column strength. Now in the Eurocode, it's different than that. In the Eurocode equations, rather than having F critical or Fn here in these equations, Eurocode basically says we're going to get effective widths based on Fy to get a cross-section strength. Once we have a cross-section strength, life is good. We need to apply a chi factor to the cross-section strength to get a reduction for member overall stability effects. So two different approaches. I'm very interested to find out which way is the new Indian standard going there. Is it going more Eurocode or going more to the American code approach? So rather than get lost in those equations, it's good to do an example to kind of understand how the equations work. How do we apply the equations? So again, my apologies again, I didn't convert these from imperial units to SI. It's a W24 by 55, so 24 inches nominally deep, 55 pounds per foot in weight. A992 steel, so Fy would be 345 megapascals. We have a flange slenderness B over T, or BF over 2TF at 6.94 for this section. And we can compare that to lambda RF. The value we looked at earlier for that is 0.56 square root of E over Fy, 13.4. It's less than that, so it's a non-slender flange. We don't have to worry about local buckling when we're looking at the flange. But we really don't need to do that check at all, because I already told you that if it's a rolled wide flange section, there are no rolled wide flange sections for grade 50 steel that have slender flanges. So we don't really need to check it. We're just demonstrating it here. For the web, the case can be very different, and the W24 by 55 is really more of a beam section. Its H over TW is 54.6, and the non-slender web limit, 1.49 square root E over Fy, is 35.9. So, oops, we got to deal with potential local buckling here. Okay, All right, so now let's suppose the column is 20 foot long, so KLX is 20 feet, but we're going to brace it in the middle, say by, okay, so I should have done it with the with KLZ equal 20 feet, but I did. So we're assuming we're putting a brace in the middle that's restraining twist and restraining flexural buckling. Okay? So by doing that, KLZ is equal to KLY. I don't need to worry about torsional buckling. That makes that much simpler. So we need a few properties. If I grab properties from the manual tables for this section, and if we calculate a KL over R for major axis flexural buckling, that's 26.3 here. If we look at it for minor axis flexural buckling, 89.6. So clearly the minor axis buckling is more critical. It's going to give us a smaller elastic buckling stress and a smaller column strength. No need to check torsional buckling here because KLZ is equal to KLY. We can see flexural buckling governs about the Y. So we'll calculate our FE using the Euler equation, pi squared E divided by KLY over RY squared. We got 35.7 KSI. All right, so now we take the ratio of FY to FE. Again, take the square root of that, and we've got a lambda. That's 50 to 35.7, 1.4. So that falls within the range of the AISC inelastic part of the buckling curve for the column. So the exponential equation on the second line here is the AISC column buckling stress formula. Again, I need to update my slides. In the current AISC standard, we call this FN now instead of F critical. So this is 27.8. For the flanges are non-slender, so we can use their full width. However, we need to check to see whether the web, whether we need to take any reduction due to local buckling in the web. Now again, if we're designing by Eurocode, we're going to take a reduction. We're going to get a cross-section strength based on Fy, and that slender web is going to say, is going to give us a reduction. In the unified effective width approach, the logic is, but wait a minute, if this column is long enough, my stress is very low at very of the column, and I'm not getting any local buckling action. And so this check here, the inequality, is basically checking for that. So we do a lambda R, that's our non-slender limit, 35.9. And then we check our H over TW, lambda, of the web. That's 54.6 for this section. Is that greater than lambda R times square root of Fy over Fn? Well, that number is 48.1. It is greater. So it means that, yes, we are going to have to calculate an effective width of the web here to do our capacity. If that came out less, I'd say my web is fully effective, then my column strength is Fn times Ag. All right, so now, since I need to deal with an effective width, in the AISC provisions, we use this is the equation that's provided for the flange local buckling stress. Is just a fancy way to write the theoretical elastic local buckling stress as a function of lambdas of R. So we got 37.1 for the elastic buckling stress, theoretical elastic buckling stress. The H is lambda times TW. Now in the American design property tables, the property tables give you the lambda for the web, 54.6. They don't actually give you the H of the web. The H is between the insides of the fillets. And so if you want H, you have to basically multiply lambda by TW. That's 21.6 here. And now we're finally ready to substitute into the AISC version of Winter's formula for a web of an I section. So C1 equals 0.18 rather than 0.22. And we have a ratio of FEL to FN that from the column, which we calculated on the previous slide, is 27.8. So the fully effective width of the web is 21.6. This W24 by 55 needs to take a minor reduction there. The effective width is a 19.8. So now we could do a width times thickness on all the elements and add them up, but if we do that for a rolled section, we just left out the web flange fillet areas. So we like to try to keep those because they're measurable. And so the way to do that is that we have the property tables that give us the gross area, and so we're going to determine, okay, what area do we need to take out because of the loss of effective width? That's H minus B sub B times TW. So we take that area out to get an effective area. And once we have that effective area, we multiply by FN, hit it with our phi factor of 0.9, and we get 388 kips. If we were to go back to the 2010 standard, when they had form factors, it was 398. And so here we can say, well, what's 10 kips among friends? We're good.